this is our quick review we did on Tuesday in class about chapter 16, which is about solubility and complex ion equilibria. Now, the symbol Ksp is called the solubility product constant, or sometimes just solubility product. It's an equilibrium constant, something we've been talking about for the last 3 previous chapters, okay? So it's not so foreign to what we've been doing. It's temperature dependent for each solid. So if you look on page 761 in the textbook, there in table 16.1, there are a lot of values listed that you might be given. You might have to solve for that value, something like that, okay? But it's not something that you have to memorize. It's something that you would solve for. Just like how, so we're talking about equilibrium, right? So it's just like when we had before, we would have our A plus B equals C, or changes into a product, right? And we would have the coefficients in front. Please excuse my terrible handwriting on the computer. But so then we would have the K of the equilibrium constant would be equal to products over reactants. So we would take the concentration of the products raised to the coefficient power over the reactants raised to each of their coefficients. And then we would solve using this. And we've done this with acids and bases. We've done this all sorts of ways for probably a good couple months now. So the same rules apply. But here, the solubility is when you have a solid that is dissolving in water. That's the whole premise, is you're taking a solid and you're dissolving in water. So remember, when we did the KEQs, we only included aqueous and gas, because those are the things that can have concentrations change. So we're not going to include still anything that's solid, anything that's liquid. We're only going to include aqueous ions now, okay? So it's going to be the same process, but it's just Ksp. It's going to be the solubility product now, okay? Now, also, the solubility product is different from just regular old solubility, and that regular old solubility is an equilibrium position. So how soluble will something be depends on its situation. Or if you change the equilibrium, then it will shift in the other direction. Okay, so let's see that with an equation. First, we have sodium chloride. So sodium has a +1 charge, and chloride has a -1 charge, so that would be NaCl, right? So let's say that you have a jar, or you have just some sodium chloride sitting around, and it's solid, so you want to add it to water. Okay, so then when you add it to water, then it will start to break apart. And so this means, like, add water. Add it to water. But we're not going to consider water because water is liquid, so it's not going to change its concentration. Well, when it breaks apart, when it's dissolved, it will break apart into its sodium ion and its chloride ion. So that would be the expression for when you dissolve sodium chloride. Now, initially, you're going to have a mass of your sodium chloride solid, but then it will dissolve, and so initial concentrations will be 0 for the 2 ions, but eventually they will change until it reaches equilibrium. So that's where we can use the Ksp, the solubility product, with this, okay? So to write the solubility product equation, the Ksp is equal to the products raised to their powers. Well, this is a balanced equation, so they're not going to be raised to anything. It's going to be raised to 1. So you have the concentration of the sodium ion times the concentration of the chloride ion. Now, I said this in class. I don't know if they would take off for not putting charges on ions in the AP exam when they're grading it, but I would strongly encourage you to do that so that you don't have to worry about that. Okay, so this would just be your expression for the Ksp for sodium chloride. Now, let's say you don't have just a +1, -1. So for calcium fluoride, calcium has a +2, and fluoride ion has a -1. Do not put Fl, I would get so mad at you. So the formula for calcium fluoride is going to be CaF2, because we need 2 fluorides to balance out that calcium charge. Okay, so then it breaks apart into its ions, the calcium and the fluorine or fluoride ion. Sorry, these are getting pretty long. But this is not a balanced equation yet. Okay, so we still need to make sure it's balanced. So the 2 fluorides have to be balanced, so we put a 2 as a coefficient in front of the fluoride ion. Okay, now how this would go into your Ksp for this, you would have still each ion multiplied, concentrations multiplied. The calcium is still raised to just 1 power because it has a coefficient of 1. But this time, the fluoride is going to be squared. Okay, so now with the Ksp expression, we can still do ice charts. We can still do initial concentrations and do the change and figure out what it is at equilibrium and solve for X or solve for Ksp or anything like that. So it's the same process as what we've been doing. I'm just showing you that you don't include the solid in your Kxp expression, which is something that's not foreign. We've done that before. But the products will always be aqueous ions when you go. Okay, so now I'm going to do example 16.1, which is on page 760 in your textbook. So you're more than welcome to just go and look at that. But I know sometimes reading the textbook might not make sense, right? So if we talk through it, maybe that will make better sense. So copper 1 bromide has a measured solubility of 2.0 times 10 to the negative 4 moles per liter at 25 degrees Celsius. We want to calculate its Ksp value. Okay, well, first thing we need to do is write out the formula. So copper 1 means that copper has a +1 charge, and bromide has a -1 charge. So that was just going to be CuBr, which commonly we come across copper with a +2 charge, so that's a little different, but that's okay. So since it's +1 -1, that's nice. We have 1 of each ion as the products when it has dissolved. Okay, so now I'm going to take you through as if this was an ice chart all the way through. Okay, so we have our I, we have our C, and then we're going to have our E, our equilibrium. So initially, now we don't have anything, but initially the concentrations of the ions are 0 because it's all in grams of solid. Now remember, we're not going to include the solid at all because it doesn't change concentration, okay? But this is just showing how our ice chart's set up. Now, we have to add towards the zeros in our ice chart, right? So we're going to add X. We would multiply by the coefficient, but there's no coefficient, so it's just plain old X. So at equilibrium, each of their concentrations equals X. Okay, now, our Ksp equation would be the concentration of this copper ion times the concentration of the bromide. Okay, now this 2.0 times 10 to the negative 4th moles per liter, that is not the value of Ksp because we're solving for Ksp. So that is the solubility at equilibrium. So that is actually what X equals. 2.0 times 10 to the negative 4. Okay, so now, does it seem like we did this whole ice chart for nothing? Yes, but just seeing that in your mind again might be helpful, and so that's why I wanted to plug that in like that, okay? So now, up here, I'm going to plug in, and I hope this makes sense since they're both equal to X. I'm just going to take the 2 times 10 to the negative 4th squared and then that is equal to our Ksp. Okay, so the Ksp answer is 4.0 times 10 to the negative 8. Now, units on Ksp values are usually omitted. You don't have to worry about that, so that would just be the answer, okay? Now, so that's just plain old solving for Ksp, plugging in some numbers, no big deal. Now, the next one we're going to do is example 4, which starts on page 766, and this does a couple things. One, it's not just a balanced equation because we're using calcium fluoride like we saw before. And 2, it has the common ion thing that we dealt with when we had buffers in chapter 15. Okay, so we should know what we're doing, but we're going to walk through it. So we're talking about calcium fluoride, which we just talked about calcium fluoride a little bit ago. So we know that calcium fluoride is CaF2. So this solid breaks down into 1 calcium ion, and then we put the coefficient of 2 in front of the fluoride ion so that it's still a balanced equation. Okay, now we're given the Ksp value and we want to calculate the solubility. So that means that we're going to solve for X in our ice chart. Okay, we want to know the concentration at equilibrium for our ions. So it's not solving for Ksp this time. So we need an actual ice chart, okay? And it's going to do some work for us. So, and remember again, you don't include the solid. It's just there, okay? Initially, we have 0 for a concentration of the calcium. But now we have this common ion deal. We have sodium fluoride. Okay, well, where is that important? Well, let's think about how we talked about the ions present in the solution, or I'm blanking right now on what we listed in chapter 15 about what ions are present. But so just thinking about what's present in the solution, we have the calcium fluoride, we have water, we have when the calcium fluoride breaks up, we have calcium ion, and we have fluoride ion. And then this sodium fluoride solution means that it's not just plain old water that we're dissolving the calcium fluoride in, we're dissolving it in the sodium fluoride solution. So in addition to the water, we have sodium ions and fluoride ions floating around. Well, the sodium ion is new, but the fluoride ion is the common ion, right? So that tells us that the sodium fluoride concentration is the initial concentration of the F minus ion in the solution before the calcium fluoride breaks down. So that 0.025 is the initial concentration of the F. Okay, so that's why it's not 0. Now, just like before, we're going to add X. Now, remember when we had a coefficient previously, you bring that coefficient down in front of the X. So it's not just going to be plus X on the fluoride, it's going to be plus 2X. So at equilibrium, it's equal to X, 0.025 plus 2X for the fluoride. Okay, now our Ksp expression, should have written this, sorry, is going to be, and we had this before, so you can always look back at the notes you were taking, the calcium ion times the fluoride ion squared. Now, if this would have been a 0, we would have had to plug in 2X for the F. But since it's not a 0, then we have the whole adding the 2X to the number deal. Assumptions do work. for Ksp, just like in all the other equilibriums. So since it's times 10 to the negative 11, we can assume that we don't need to include the adding or subtracting of the x's. So in reality, it's going to be 4 times 10 to the negative 11 equals x for calcium times, now we're going to get rid of the plus 2x, so we're just going to plug in the 0.025, supposed to be no, sorry, 0.025 squared. So again, we made an assumption so that you can just solve for x that way. And when you solve for x, x is equal to 6.4 times 10 to the negative 8. Now, this is not a Ksp, so we should need to have a unit. And the unit is the same as molarity. You can say molarity, or you could say moles per liter. Either one is fine, okay? So that means that 6.4 times 10 to the negative 8 moles of solid calcium fluoride will dissolve in every liter of the 0.025 molar sodium fluoride solution, okay? And so that's an example of how you can do the assumption rule, how you can include common ions, and all of that, like things that we've done before. Now, moving ahead, you could figure out if precipitation will occur. So remember, precipitation will happen if from a double replacement reaction, 2 ions form an insoluble product. So to do this, we need to compare a number to the Ksp to determine if that will actually happen. So just like how we compared Q versus K before, we're going to compare Q, which is just, it's called the ion product, versus the Ksp, the solubility product, to determine if it will occur. So if the Q is greater than the Ksp, then the precipitation will occur until the concentrations are equal to the equilibrium concentration. Okay, and if it's less than Ksp, then no precipitation will occur. So we're going to do example 12 or 16.5, that's on page 768, to show how we can compare Q versus K to know if it will precipitate or not. A solution is prepared by adding 750 milliliters of 4 times 10 to the negative 3 molar cerium nitrate to 300 milliliters of 2 times 10 to the negative 2 molar potassium iodate. IO3 is what that is, and that's a polyatomic ion that I didn't have you memorize this year, but I think on the AP exam they will give you that. So, will cerium iodate precipitate from this solution? So they say that when you combine the cerium with the iodate, that could form an insoluble product. So we want to know if that would precipitate. So we're going to use the information to solve for Q and then compare it to the Ksp that we're given. Okay? So just like we've done before, last chapter, we need to take the moles of the ion divided by total volume to get the concentrations of each ion. So one ion involved is the cerium with a +3 charge. Okay, because if we look at our Ksp expression of our solid, so I'm just talking about this right here. Okay, so that would be the cerium has a +3, notice the 3. And then the iodate has a -1, so the IO3 with a -1. And then there's a 3 down there. That 3 means that we're going to have to raise it to the 3rd power because the solubility of that is going to be when it breaks down, you have your cerium plus your iodate. But remember that parenthesis 3 means that there's actually 9 oxygens, so you need to put a 3 in front. That looks like 310. I'm sorry for the terrible handwriting. Okay, so now we need the concentration of each ion to plug into this to solve for the right side of our Ksp. Okay, so we need to take, remember, molarity equals moles over volume, or moles over liters. Okay, now since you have milliliters, you could use milliliters and get millimoles. You know, some people like to do that, some people don't. It's up to you what you want to do. I'm gonna do the millimole route. So to get moles, you take molarity times liters. Okay, so for the cerium, I have to take the 750 milliliters times the 4 times 10 to the negative 3 molarity. And then, so that gives me moles of the ion, but then I need to divide it by total volume, which total volume is going to be our two added together. So that would be 1,050 milliliters. So remember, I'm doing like the millimole situation. So this is milliliters, and this is milliliters, so I'm good because they cancel each other out. Okay? And then for the iodate, same process. We take the 300 milliliters times the molarity of 2 times 10 to the negative 2 over total volume. And the total volume is the same, so it's still going to be 1,050 milliliters for the denominator. So the molarity of the cerium ion is 2.86 times 10 to the negative 3. And the iodate is 5.71 times 10 to the negative 3 molar. Okay, so now that we have these two concentrations, these are the initial concentrations mixed in the solution before they form together to make the precipitate. Okay, so we want to figure out, we're going to just, replace Ksp with Q, and we're going to solve plugging in these numbers for Q. So, plugging them in, we have 2.86 times 10 to the negative 3 times 5.71 times 10 to the negative 3 cubed. Okay, so then when you get that, Q is equal to 5.32 times 10 to the negative 10. No unit needed, just like Ksp doesn't have a unit. Okay, so now we have to compare Q versus K, Sp. So Ksp is 1.9 times 10 to the negative 10, and the Q is 5.32 times 10 to the negative 10. Well, Q is larger. So that means from the previous slide, since Q is larger, it will precipitate. In order for that to form the solid. Okay, so this is all we were able to talk about in class. Today was the only day that we were focusing on the solubility products, but it's a very short chapter. I wish we could have gotten to it, but we just don't have the time. So review this as much as necessary and ask me questions in class.